Hello everybody! Today we will solve a problems on the topic energy in a magnetic field. This is the goal of the lesson. At the end of the lesson, you will be able to use the equation for the energy stored in an inductor. And as always, before we start solving problems, it will be useful to recall the equations from the previous topic. So, energy stored in an inductor can be found by multiplying inductance to a current squared and divided by 2, and the energy density in any magnetic field can be found the B squared over 2 mu 0, where B is magnetic field, mu 0 is magnetic permeability of a free space. Well, let's start solving from the first problem. What we have here? Let's write the givens. So we have an inductor which has an inductance of 0.5 millihenry, and when a current of 20 amperes is passed through the inductor, we ask to find the energy stored in this inductor. Well, this is a pretty easy problem. This is the equation for the energy stored in an inductor, and all we do just put the numbers here. 0.5 10 minus 3 milli times 20 squared over 2, so it is 0.5 10 minus 3 times 400 over 2, and we can cancel this. We have 2 here, 200. This can be cancelled as 100. So 100 times 10 minus 3. The final answer for the energy is 0.1 joule. As you see, this was an easy problem, so let's move to the second problem. What we have here? We have a heating coils in a hair dryer that has a diameter of 0.8 centimeters. Let's write the givens. Diameter is 0.8 centimeters, so it is 0.08 in meters, and we have length of 1 meter and a total number of turns of 400. And how much energy stored in the solenoid if 6 ampere of current is passing through this. So again, the equation to find the energy stored in an inductor, but here we don't know what is L, and it can be found if we consider this as a solenoid. This is the equation to find the inductance of a solenoid. So mu 0, it is 4 times pi, and it is 400 squared. A, it's the area. Well, area, we don't know area. It is, we will find it later. And over L, 1 meter. So area can be found if we have a diameter. It is PD squared over 4, and it is 3.14 times diameter. It's 0.08 squared over 4. So area is equal to 0.405024 meters square, and this is 5024 10 to the minus 1, 2, 3, 4, 5 minus 5 meters squared. And we just put into the equation for an inductance 4 times 3, 14, this is pi, 10 minus 7 times 4, we can take it 400 squared, it is 1, 6 and 4 zeros, and area, as you said, 5, 10 minus 5, and all we divided to 1 because the length is 1 meter. And what we have here, so this is actually 1.610 sorry, this is actually 1.610 minus 5, and we see that we can cancel here minus 5. And what we have L as a 4 times 3, 14 times 1.6 times 5,004 over 1 and 10 minus 7. Well, L is equals to, if we multiply all this, it will be 100. So L is equals to 100 times 10 minus 10, it is 10 minus 5 Henry. Now we put to this equation for the energy and find the final answer. Energy is equals to 10 minus 5, current is 6 to the squared over 2, so this is 18, 10 minus 5, and I can write in this form 1.8 10 minus 4 joules. So this is the answer, and let's move to the third problem. So what we have here, let's write into the given. Well, we have 200 turns of solenoid. Current here is 175 ampere, and it produces a magnetic flux of 3.7 10 minus 4 Tesla to the meter square, or we can write as a Weber, but this is in each turn, so the total flux is 200 times this, and we're asked to find an energy here. Well, as always, I will start with an equation for the energy stored in an inductor, but here I don't know L, and L can be found by using this equation. I don't know, do you remember this equation? So this is from the inductance. Inductance will be N times flux over I, or we can find this equation by using this, and also for the solenoid mu0 N over Li. So by combining these two equations, actually you get this. So I'm just choosing the easy way. If you combine these two equations, you get this equation. So let's find what is L. N, it is 200 times flux 3.7 10 minus 4 over current, it is 175. And what we can do here, so 200 and this is minus 2, we just calculate what we got here for the L. It is approximately 423 10 minus 2 Henry. And that's it. If we know the inductance, we can easily find the energy. 10 minus 2, the current 175 squared over 2. So here I need to use a calculator. So the final answer is approximately also 0.04648 joules. Well, this is an answer, and we'll move to the final problem. What is given here? The magnetic field inside the superconducting solenoid, the field is 4.5 Tesla. So this is a pretty huge field, you should note it. And inner diameter, it is 4.2 centimeters, which is 6.2 meters. And the length is 26 centimeters. It can be written as 0.26 meter. And we are asked to find A, the magnetic energy density, and the energy at all stored in the magnetic field within the solenoid. Well, again, what we do here, at A part, we're going to find the magnetic field energy density, and this is B squared to mu 0. So we know everything here, we can find it directly. B, it is 4.5 squared over 2, 4 pi 10 minus 7. So 4.5 square, it is 2025. Here we have 8 times 3, 14, 10 minus 7. So also, if you use the calculator, you can find it that this is 0.08 06 10 to the power 7, because this is just going to here as a 10 to the 7. So it will be joule to the meter cube. And I can write in this form 80610 to the power 6 joule to the meter cube. This is the answer for the A part. And for the B part, we know that the magnetic field density is energy over volume. So if you want to find an energy, it will be field density, energy density to the volume. And the volume can be found as area of the solenoid times L. We don't know area, but we know the diameter, so it is PD squared over 4 times L. So let's calculate. 314, diameter it is 0.062 square over 4 times the length is 0.26. So again, if you use a calculator here, the volume will be equal to 0.00407,846 meter cube. So to find an energy, we need to multiply this. So this is actually 7.846 1, 2, 3, 4, 5. 10 minus 5 multiplied to the 8.06 10 to the 6. So if we can say it here, we have just 10. So finally the answer here is approximately 6.32 kilojoules. So we get a big amount of energy because the field is very big. Well, this is the last problem. I hope you have enjoyed solving problems with us. If you like our video, please subscribe and share. Thank you.